So the moivres theorem, here we go. We actually know it already, if you think about it. Because we already talked about the different rules when playing with the modulus and the argument. And all the moivres theorem is really saying is, when you raise a complex number to the power of n, you multiply the argument by n. And that's all it's really saying. So cos theta plus I sine theta to the power of n is cos n theta plus I sine n theta. So really nothing new. You'll notice the modulus for de Moivre's theorem is 1. But we can extend that out because we've also seen that when you raise a complex number to the power of n, then its modulus gets raised to the power of n. So we can extend that out to be r to the power of n cos n theta plus I sine n theta. So if I want to find 1 minus I to the power of 5, okay, we could expand the whole thing out and then collect like terms and we'd get an answer. It would work. Obviously, the higher the power, the more work involved. De Moivre's theorem allows us to do it a bit quicker. So modulus of z is the square root of 2. The argument is minus pi and 4. So if I change it to mod-arg form, get root 2, and the argument's minus pi and 4, all of that to the power of 5. Well, root 2 to the power of 5 is, what's that going to be? 4 root 2, isn't it? So that'll be 4 root 2. And the argument, minus 5 pi on 4, well, let's get it into the range that we want. We want between minus pi and pi. So if we've gone backwards, minus 5 pi on 4, that's the same as going 3 pi on 4 the other way, isn't it? So we end up with 4 root 2 cis 3 pi and 4. That's the answer in mod-arg form. If we actually wanted to work out in Cartesian form, then we could go and say, well, what's the cos of 3 pi and 4? What's the sine of 3 pi and 4? And there's our answer, minus 4 plus 4i. This gives us another way of finding not only the square root, but any roots, cube roots, fourth roots, and so on. So if we think of de Moivre's theorem, if z to the power of n, we know the answer is x plus iy. So now I'm saying z to the power of n is r cis theta. What was z? Then I must have gone back the other way. Well, we know when we find the root of a number in index form, that's 1 over whatever root we want to find. Square root, the power is a half, cube root, the power of a cube, and so on. So if we apply de Moivre's theorem, then the argument would be divided by whatever the root is we're trying to find. And of course the modulus will be the nth root of the modulus. Now of course roots will have many answers. So what we do is we say, sure, that would be one answer, but I could keep going around the circle. Now we don't add the 2 pi to the theta on n. We add it to the theta first, then divide by n. And however many times we need to go to get the number of solutions we need. Now, if you know the solutions are in conjugate pairs, you don't have to use 0, 1, 2, 3, 4, 5. Any consecutive numbers will work. So if you know they're in conjugate pairs, then spacing it around 0 is a sensible thing to do. Because the plus or minus 1 and the plus or minus 2 will create the conjugates that you need. All right, let's find the square root of 4i then. So z squared is 4, well, cis pi and 2. So my answer will be 2 cis, 2 pi k plus pi and 2. All of that divided by 2. I need 2 solutions. So I'll just go with 0 and 1, so 2 consecutive numbers. And we end up with 2 cis pi and 4, 2 cis 5 pi and 4. That one we can then work out if we wanted to. Or keep going. There we go. Root 2 plus root 2i and minus root 2 minus root 2i. The interesting things about roots is they're always evenly spaced around the circle. So when you're talking about square roots, they will always be 180 degrees away from each other. So that's why when you're finding the square roots of a real number, square roots is probably a bad way of saying it. If you've got x squared equals a real number, you end up with plus or minus. They're 180 degrees away from each other. And sometimes that's an easier way of getting the answer. So for this one, well, they're not on the real number line, but once I find the first one, I know if I'm finding square roots, 180 degrees away will be the other one. So that's another way of doing it. Just find the first one, and you know they're going to be evenly spaced around the Argand diagram. But yes, we're no longer restricted to square roots now. We can use this for any root. I want to find the 4 roots of 16. Now, when we were dealing with real numbers, it would have just been plus or minus What's the 4 through to 16? It is 2, isn't it? Yeah. I would say plus or minus 2, and we would have thought there's only 2 answers. But there's actually 4 answers. It's just 2 of them are imaginary. So x to the power of 4 is 16. Well, 16 cis 0. So it'll be 2 cis 2 pi k on 4. Notice, because it's real, 16 is a real number, I said I know the solutions are going to be in conjugate pairs. I want 4 consecutive numbers, so I'll do it around 0. So I've got 0, plus or minus 1. Now, whether I choose plus or minus 2 doesn't really matter. I'll tend to go with a positive. So, and 2. That gives me 2 cis 0, 2 cis pi on 2, 2 cis minus pi on 2. There's your conjugates. And 2 cis pi, there's our answers. But I say we could do it now and say, well, look, I know that the 4 through to 16 is over there at 2. They've got to be evenly spaced, so every 90 degrees I'm going to have a solution. So there'll be one up there at 2i, down the bottom at minus 2i conjugates, and over there at negative 2. So find the 4 roots of 1 plus root 3i. So 1 plus root 3i is 2 cis pi and 3. 4th root of 2, well, we can't work that out. And then we'll have pi and 3, and this time it's not a real number, so I'm not going to worry about conjugate pairs. I'll just go 0, 1, 2, 3. And there we go. And that's what we were just talking about. We've got pi on 12, 7 pi on 12, 13 pi on 12, 19 pi on 12. I suppose we could calculate the exact value by playing with sum and difference of angles if we really wanted to, but I don't want to. So leave it in mod-arg form for this one. Oh, use the principal argument. The principal argument is when it's between minus pi and pi, the way we've defined it. With our diagram, okay, I know my first solution's over there, but again, 4 solutions in 360 degrees, every 90 degrees, I should find a solution. So there'll be one up there at 7 pi and 12, then minus 11 pi and 12, and minus 5 pi and 12. There'll be our 4 solutions. Oh, look, they line a circle. Hey! 3A.